Sorry, the last video got cut off. Okay, so just continuing on. So wanted to just take a few examples of what you can do with mass spec data. So let's say you're given a mass spec that looks like this. So we can assume the peak furthest to the right is the parent ion peak, because that's going to be the molecule that has the most mass, right? If anything breaks off the molecule, it's going to have a smaller mass. So the peak furthest to the right is the parent ion peak. So if we see a spectra like this, where you have a parent ion at 162 and nothing else, so first of all, it's not odd. So no nitrogen, unless there's an odd number of nitrogens or an even number of nitrogens, but I won't do that to you unless I tell you. There's no M and M plus 2, so no isotope peak. So that means there's no chlorine or no bromine. And since we're only working with molecules that have carbon, hydrogen, oxygen, nitrogen, what else do we say? Chlorine and bromine. So if there's none of those, then you only have to worry about carbon, hydrogen, and oxygen. Okay, so what can we do with this? So what we're going to do with this, we're going to take the 162 and divide it by 12, right? Why 12? Because that's the mass of carbon. So you have to be able to do long division math. So if you remember how to do this, you can't use a calculator. So a remainder of 4, bring the 2 down, so that goes 3 times, right? 36. If I did my math right, with a remainder of 6. Okay, so this is the number of carbons, and the remainder is the number of hydrogens. So a molecule has a molar mass of 162. One possible formula is C13H6. And so what we want to do is generate other formulas. And so the way that we're going to do that is we're going to take away, so if you set this up the same way that I have mine set up, so I should go horizontal, take away 1 carbon, and and add 12 hydrogens. So take away 1 carbon, which weighs 12, and replace that with 12 hydrogens, so the mass stays the same. So C12H18 would also have a mass of 162. And then let's do it again. Minus 1 carbon, add 12 hydrogens. So C11H30 also has a mass of 162. And so you only need to do that until have twice as many H as hydrogens as carbons. And it'll become apparent in a little bit. Okay, and then we want to go vertical and get other formulas as well. So when we go vertical, we're going to take away 1 carbon and 4 hydrogens, and we're going to add 1 oxygen. So 1 carbon's 12, 4 hydrogen 4, so that's 16. Oxygen has a mass of 16. So if we go to C12H2O, that would also have a 60. And so then we want to do that for these formulas as well. So C11H14O, and then C10H10O. So you want to keep doing that until you run out of carbons or hydrogens. C9H6O2, and that O3. C8H2O4. So all of those have the same mass. And then do the same thing here. So C10H26O, C9H22O2, and C7H14, 14O4, C6H10O5, and again do that until you run out of something. Okay, so all of these formulas would have the same molar mass. So if you had a mass spec that looked like this with the parent ion peak of 162, and you knew the molecule could only have carbons, hydrogens, oxygens, nitrogens, chlorines, or bromines, then this is all of the possible formulas that could possibly be. So that's pretty powerful to take some totally unknown sample, do a mass spec, which you could do in 5 or 10 minutes. And now you've got it down to these possible formulas, and then we're going to reduce these formulas even further. So let me show you how to reduce these formulas further. Let me get this out of the way. Okay, so let's calculate double bond equivalencies. So using this formula, CnH2n plus 2 is a theoretical number of hydrogens minus the actual number of hydrogens, and then we're going to divide all of that by 2. So if we took this formula C13H6, for example, so if n is 13, so 2 times 13 plus 2, so that would be 28, is a theoretical number of hydrogens. So if you had 13 carbons, you could put 28 hydrogens on them, and then every single carbon would be saturated with hydrogens. So minus the actual number of hydrogens, so 28 minus 6, and then divide that by 2. So we get 22 divided by 2 equals 11 double bond equivalencies. So this one has 11 double bond equivalencies. And if you did all of your formulas correct, when you go down a column, and if you set it up like I have mine set up, then it works out nicely like this. As you go down a column, the double bond equivalencies go up by 1. And as you go horizontal to the next column, they go down by 4. So they go down by 7. So 11 minus 7, so this formula would have 4. So this would have 5, 6, 7, and 8. And then if we go from C12H18 to the next column, it goes down by 7 again. So this would be negative 3. And then negative 2, negative 1, 0, 1, 2, 3, and 4. Okay, so what does it mean to have negative double bond equivalencies? It means that these formulas cannot exist. So now you've narrowed it down even further. So these are the only possible formulas that remain. So your molecule, which has a molar mass of 162, is one of these formulas that remain. So then how could you narrow it down further? You would need other forms of spectroscopy, like mass spectroscopy and NMR spectroscopy, and that would allow you to narrow it down to one possible formula. Okay, so just to remind you, so what does it mean for double bond equivalencies? So if a molecule has one double bond equivalency, that means it has one double bond. And since this is only carbons, hydrogens, and oxygens, that means it could have a carbon-carbon double bond or a carbon-oxygen double bond, not both. Or it could have one ring. And if it has a ring, then it doesn't have a double bond. Right? If it has two double bond equivalencies, then it could have two double bonds. So it could be two carbon-carbon double bonds, two carbon-oxygen double bonds, or one of each. Or it could have one double bond and one ring, or it could have two rings, or one triple bond. Right? Okay, so the number of double bond equivalencies gives you information. So for example, if we deduce that our structure was this formula, C5H6, let's pick an easier one. That's a lot of oxygens. Let's pick this one. So C10H10O2. So let's say we deduce that was our formula through other data. And we have 6 double bond equivalencies, right? So that gives you information. So I could come up with a molecule. Let's see. So that's 6, that's 10 carbons. 1, 2, 3, 4, 5, 6, that's too many double bonds. So 1, 2, 3 double bonds, 2 rings, that's 6 double bond equivalencies. So that's all my double bond equivalencies. Let's stick a couple of oxygens on here. And let's not put one there. Let's put one here and here. We could have put them anywhere. So that should be 10 hydrogens. So let's see. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So that's C10H10O2, and it's got 6 double bond equivalencies. So the point is that that gives you information about the structure of your molecule. And that's one whole purpose of spectroscopy and organic chemistry, right? It serves several purposes. One purpose is to figure out the structure of your molecule. So every single thing that you learn doing spectroscopy is information that you have to keep in mind. 6 double bond equivalencies tells you something about the structure of your molecule. Of course, there could have been lots of molecules that we could have come up with. That's just one example to illustrate the information that it gives you. Okay, so what if our mass spec looked like this? And so we got some fragment peaks, but for our purposes, we'll just ignore them. And we'll just focus on the molecular ion peaks. So this is M and an M plus 2. And so we have an M and an M plus 2 and a 1-to-1 ratio. Whoops. What does that mean? That means this molecule has bromine in it. Okay, so we're going to take the 200. If we can work with either, we could take the 200 or the 202. If we take the 200, the first thing we're going to do, so if you remember, bromine comes as 2 isotopes in nature. Bromine 79 and 81. If we take the 200, then we're going to subtract off 79 for the lower mass isotope. If we take the 202, then we're going to subtract off the higher mass isotope. And it doesn't matter which one you use, because you get to the same spot. Right? So you just have to remember, if you're using the lower mass, subtract off the lower mass isotope. If you're using the higher mass, subtract off the higher mass isotope. So then we're gonna do something similar. We're gonna take what's left and divide by 12. So that goes 10 times with a remainder of 1. So one possible formula is C10H1, and don't forget the bromine. C10H1 bromine is one possible formula. And then let's get other formulas. So we go that way, minus 1 carbon, add 12 hydrogens. And do that until you run out of, until you have twice as many hydrogens as carbons. So then add another 12. And then go vertical to get formulas with oxygen. So C8H9BRO, C7H5BRO2, C6H1BRO3, and same thing here. Okay, and so there's one way, several ways that you can check to make sure you didn't make a mistake. So one way is, if you notice, all of these N and the same number of hydrogens. So if you don't end up in the same number of hydrogens at the bottom of a column, you made a mistake somewhere. Okay, so that's all of the possible formulas. Let's calculate double bond equivalencies. So when you do this, if you have a chlorine or a bromine in your formula, add 1H to actual. So when you're calculating double bond equivalencies, add a hydrogen if you have a chlorine or bromine to your actual number of hydrogens, because bromine takes 1 bond just like hydrogen does. Okay, so we have 10 carbons, so 2 times 10 plus 2. So you could have 22 hydrogens if you had 10 carbons. And then we're going to subtract off the actual number. So 22 minus 2 is 20, and then we're going to divide that by 2. So this first formula has 10 double bond equivalencies. And then as we go horizontal, it goes down by 7, so that's 3. And then this is -4. And then as we go vertical, if you set it up like this, it goes up by 1, so 4, 5, and 6. And -3, -2, -1, 0, 1, and 2. So then all of these that are negative are not possible. So 1, 2, 3, 4, 5, 6, 7, 8 possible formulas if your mass spec looked like that. Okay, and then one more example. So what if your mass spec looked like this? So what is significant here is that this is odd. So that means nitrogen is present. So what we're going to do first then is take the 131 and subtract off 14 for the nitrogen's mass. So 117 left over. And then take the 117, and now everything else is the same. Divide that by 12. How does this go? 9 times. So 9 times with 9 left over. So C9H9, so that's the number of carbons, number of hydrogens, and don't forget your nitrogen. So that's one formula. Or we could go C8H, so 1221N, right? So that's another possible formula. And then get formulas with oxygen. Okay, so that's all of the possible formulas if you had a mass spec with the molecule with a molar mass of 131, assuming we're limited to carbon, hydrogen, oxygen, nitrogen, chlorine, and bromine. So you know there's no chlorine and bromine because there's no M+2 peaks, so no isotopes that you have to worry about. Okay, and then lastly, how do you get double bond equivalencies if there's nitrogen present? So for calculation of double bond equivalencies, you'll just take one hydrogen away from the actual number of hydrogens. So if we take this first formula, CNHN, or C9HN9, so 9 times 2 plus 2, 20 is theoretical. And then minus 8. So we're going to take one away because of the nitrogen, so that gives us 12 divided by 2 is equal to 6 double bond equivalencies. So if it did everything right, that should have 6, so this 7, that should have 8, so this would be -1, 0, 1, 2, 3, and 4. So another way to check yourself is take the very last formula, calculate in each column, calculate the double bond equivalencies, and you better get 4 in this example. So 3 times 2 plus 2 is 8, minus 0 because we took one away, so 8 divided by 2 is equal to 4. So if our double bond equivalencies worked out right, then we know we did not make a mistake somewhere and accidentally subtract the wrong number of hydrogens or forget to subtract a carbon or something like that. Okay, that's all.